Hi everyone, my name is Lucas Hu, and today I'm going to be presenting our paper which is titled Model Generalization in Deep Learning Applications for Land Cover Mapping. First, a bit of an introduction. The UN has estimated that approximately 20% of the Sustainable Development Goal indicators can be interpreted and measured either through the direct use of geospatial data itself or through integration with statistical data. Relevant for this paper, land use/land cover data, which is a type of geospatial data, is useful in many downstream sustainability applications. For example, urban development researchers can use land cover data to study the expansion of urban buildup over time and the disappearance of forested or natural landscapes. With recent successes in deep learning, it is natural to cast these modeling problems with geospatial data, such as generating land cover maps from satellite imagery, as shown here, as vision problems, and then apply state-of-the-art methods on them. This strategy poses several problems from a machine learning perspective, though. First, most existing state-of-the-art computer vision methods have been developed for natural images, such as pictures taken with a camera, and may be suboptimal when applied to geospatial images. Second, ML model generalization is usually measured on a held-out dataset that is assumed to be drawn from the same distribution as the training dataset. With geospatial data, this assumption can be violated in many ways. Imagery from a given satellite can vary based on location of the image, time of day, time of year, atmospheric conditions, and even geolocation errors. So explaining how a geospatial model generalizes, or does not generalize, is a valuable exercise to show the ML community. Therefore, we seek to answer three main research questions. First, how well do models trained on one season generalize to other seasons? How well do models trained on one continent generalize to other continents? And what features or indicators might we use to predict when model generalization will be poor? We test our three research questions with the CEN12MS dataset, which is made up of satellite imagery sampled from various scenes across the globe. Each scene contains data from one particular region on Earth from a particular season. Each scene is composed of hundreds of patches of satellite imagery. A single patch represents a 2.56 kilometer by 2.56 kilometer plot of land in the real world. Each patch is represented in the dataset as a 256 by 256 pixel image. In total, the dataset has about 180,000 such patches across its 252 scenes. Each pixel in each patch contains data from three distinct sources. First, Sentinel-1 synthetic aperture radar measurements. 2, Sentinel-2 multispectral measurements, including RGB and infrared. And 3, land cover labels, or a classification of each pixel into one of several different land cover categories. For example, water bodies, forest, urban land, etc. Note that these labels have been upsampled to match the resolution of the inputs. As a result, the labels are actually quite noisy, which should be kept in mind when interpreting the model's performance on the image segmentation task. For the semantic segmentation task, we selected a fully convolutional dense-net model based on its success in previous work. For the forward pass, we pass in all Sentinel-1 and Sentinel-2 bands from the 256 by 256 patch as input and produce a land use mask as output. To measure cross-continent model generalization, we train a model on all scenes from within a given continent, withholding 20% of the within continent scenes as a validation set, and then evaluate that model on each scene from all other continents. We then compare the model's performance on the withheld within-continent scenes to the model's performance on out-of-continent scenes. The cross-season case is analogous to the cross-continent case. We train on all the scenes from a given season, and then evaluate the performance on scenes from all other seasons. Here, we can see the results for both the cross-continent and cross-season model performance experiments. Each row shows the results for a single model trained on a given continent or season. Each column shows the results for the model when evaluated on a given continent or season. Each value in the table represents an overall accuracy metric, i.e. percentage of pixels in the image that were correctly classified, averaged over each scene in the per continent or per season evaluation set. The diagonal entries represent the model's accuracy on the 20% validation set from within the same continent or season. Looking at the results on the whole, some general trends start to emerge. In both the cross-continent and cross-season cases, it appears that overall accuracy is generally highest when evaluated on the same continent or season on which the model itself was trained. In other words, out-of-continent or out-of-season accuracy tends to be lower than in-continent or in-season accuracy. More generally, there appears to be a high degree of variability in model performance across different continents or seasons. This suggests that just because a model accurately predicts land use classes in one continent or season doesn't necessarily mean that it will accurately predict land use classes in a different continent or season. These differences in model performance can sometimes be quite drastic. The DenseNet model I was trained on scenes from Europe, for example, had a mean accuracy of 0.79 when evaluated on validation scenes from within Europe, but only a mean accuracy of 0.51 when evaluated on scenes from Africa. Next, we investigate the underlying reasons behind this lack of geospatial generalization. We focus on the problem of cross-continent generalization due to the discrepancies in landscapes between different continents. We hypothesize that a key factor that makes geospatial generalization difficult is that each continent may have significantly different input distributions, indicating the presence of different landscapes. For example, South America might contain more satellite imagery of rainforest landscapes than Europe does, making it difficult for a model trained on images from South America to perform well when classifying land cover in Europe. To test this, we first investigate the differences in images between continents. In this figure, we show kernel density estimation plots for all Sentinel-2 bands across different continents. It appears that each continent seems to display a relatively unique signature as characterized by the distribution over each input band. This suggests that by looking at the band distribution of any given image and comparing it to the band values observed in each continent, we may be able to infer which continent, or which type of landscape, the image is more likely to belong to. In other words, looking at the band distribution of a given image may help us determine if a given image is quote-unquote in distribution or not, relative to the other images in the continent. To help further visualize this idea, we cluster all images in the entire dataset according to the means of each sentinel band over an entire patch. Since there are 10 input bands in total, we represent each image by a 10-dimensional vector. We then fit a k-means model with k equals 16 clusters on these 10-dimensional vectors. The most representative images for each cluster are shown in the figure below. As one can see, each cluster seems to represent a unique type of landscape. For example, clusters 0, 5, and 10 represent more desert-looking landscapes, whereas clusters 2 and 9 represent snow or tundra. If different continents do indeed have different types of landscapes, then we should expect that the distribution over these clusters will differ between continents. To show that this is indeed the case, we then compute the cluster that each image belongs to and find the histogram over these image clusters for each continent. As an example, South America seems to have a higher prevalence of cluster 14, which appears to be a more rainforest-type landscape. Australia seems to have a higher prevalence of cluster 11, which seems to represent a more arid or outback-type landscape. After normalizing each continent's cluster histograms, we can also apply PCA on these histograms to visualize which continents are most similar or different to each other. Looking at this PCA plot, we can see that Africa and South America tend to have similar landscapes. Europe and North America, too, are relatively similar. This may explain why, in our cross-continent results table, the model trained on Europe was able to perform pretty well when evaluated on North America, and why it performed so poorly when evaluated on Africa. Australia's landscapes in the bottom right are unique relative to all other continents, which may also explain why no other continent models were able to perform well when applied to Australia. And lastly, Asia appears to occupy a nice little middle ground between all continents, which seems to fit our intuitions pretty well. Finally, we can use these per-continent histograms to also infer the probability of the continent given the cluster that the image belongs to. As one can see, certain landscape clusters are indeed far more likely to belong to certain continents than to others. For example, clusters 5 and 10, which are more desert landscapes, almost exclusively belong to either Africa or Asia. Clusters 9 and 2, snow landscapes, exclusively belong to North America. Since certain landscape clusters can be indicative of belonging to a certain continent, we may be able to take advantage of these landscape distributions to produce models that perform better in certain continents, or at least to know if a model trained on a certain set of landscape images is capable of performing well on a given continent. To summarize, in order to evaluate how well geospatial models trained on one season or continent generalize to other seasons or continents, we trained land use classification models on data from specific seasons and continents and evaluated them on data from different seasons and continents. Experimental results show that out-of-continent or out-of-season accuracy tends to be lower than in-continent or in-season accuracy, and that there is often a high amount of variability in model performance across different continents and seasons. We then applied clustering methods to patches of satellite imagery based on the input band values, demonstrating that different continents do indeed comprise visually different landscapes, which may explain the difficulties in geospatial generalization across continents. This leads to three main insights to take away. First, practitioners should exercise caution when naively applying geospatial models trained on one season or region to new seasons or regions. Two, training geospatial models on data from a diverse set of seasons and/or continents may be necessary to promote generalization. And third, when using an existing model to perform land cover classification on a new region, it is often helpful to know whether the model was trained on imagery from a similar landscape. For example, on imagery belonging to similar clusters. If not, it may be necessary to fall back to a simpler model, rather than naively applying the existing model to the new region. Finally, future work is necessary to determine what techniques may be required to promote cross-continent and cross-season generalization, and to reduce performance degradation in general when predicting on out-of-sample remote sensing data. That's it for today. Thank you very much for your attention.